All right, learning unit 10 is on drawing molecules. So I'm going to apologize ahead of time. This video is going to be a little bit on the longer side, but like we've done in the past, it'll actually be worth double. It's going to be about 25-30 minutes long, but it's going to allow us to have the most critical skill in moving forward with the next two learning units, which is learning how to draw what we call Lewis structures. So remembering that our world is three-dimensional, right? We need to think about molecules having three-dimensional structure. So if you grew up kind of with Flat Stanley, or if you ever read the Flat Stanley books, right? The reality is Flat Stanley isn't flat, right? Here's Stanley, he's not flat, right? I don't know how many of you get the Office references anymore, but that Stanley is not flat. The same is true when we think about our molecules. When we draw Lewis structures, we're actually drawing two-dimensional representations, but we have to remember that in reality, these molecules are three-dimensional. And so that's where we're moving in our second skill in this learning unit, is to think about the molecular shape. And then lastly, thinking about molecular polarity, because that has so much to do with the physical properties that these molecules have, with the chemical reactivity that they'll have. But it all starts at its core with having a correct Lewis structure. So how do we have a correct Lewis structure? What is a Lewis structure? Well, a Lewis structure, and again, I'm highlighting here that even though we're using the word structure, these probably are better referred to as Lewis formulas, because they don't give us any information on three-dimensional structure. As we'll learn in our next skill, we can use a proper Lewis structure to infer three-dimensional structure. But they really are a way that we convert molecular formulas to structural representations using electron dot symbols for atoms. We learned about those in our last learning unit. We're going to show bonded pairs of electrons as lines that connect atoms. And then we're going to have lone pairs of electrons as dots, if they're present on certain atoms. So we'll start out by drawing, and through this little video here, we're going to show all different ways that we can show different molecules, some that only have single bonds. Those will be fairly simple to represent. Then we'll talk about how we can draw molecules with multiple bonds. We'll introduce a concept of resonance structures, which is for molecules that have double bonds, we can kind of slosh around where those electrons are. And then lastly, we'll close with sort of some exceptions to the general rules that we're going to start with. All right, so what are the rules for drawing a Lewis structure? What are the steps I need to follow? We're always going to have these same steps that we use to draw a Lewis structure. 4 steps in general, and it begins with determining the number of electrons that you're going to have in your overall structure. To do that, you're just going to add up any valence electrons that you have for any of your atoms. And I'm going to highlight here that we need to add or remove for electrons if we have an ion. So if you have a cation, for example, a polyatomic cation, that would be something that has fewer electrons than the valence number would indicate. So you have to subtract whatever that charge is. If you have a polyatomic anion, in that case, you're going to have more negative charge. So you're going to be adding whatever that charge is, that number of electrons, to your total bit here. So I like to think about electrons are what are the glue that hold these atoms together. So our next step is to begin piecing these atoms together with single bonds, remembering that each bond represents 2 electrons. So we're going to start by putting our least electronegative atoms in the center, and then we're going to fill in the more electronegative atoms on the periphery. As we'll see on our next slide here, we're going to be able to use our periodic table as a great cheat sheet here to help us understand some trends with how things like to bond. So after we've accounted for any of these bonding electrons with single bonds, right, we're going to complete everybody's octet using the remaining electrons, starting with the most peripheral atoms, which those are going to be the ones that are most electronegative. But we have to remember, don't use more electrons that you have, and then anything that's left over at the end, you can put them back on the central atom. So we'll see some examples of this as we go through a few problems here. At the end, you always want to go back and just do a double check. Make sure that you have the right number of atoms in your Lewis structure as you have in your molecular formula. Count your electrons again. Make sure that you haven't had something that you drew in more electrons than you're allowed or fewer than you're allowed. And as we'll get to in just a little bit here, we want to make sure we look for anything that might have an incomplete octet, fewer electrons than it needs. And then formal charges. So we'll explain a little bit more on the next slide what formal charges are. All right, so let's actually just start with a pretty simple example here. Keeping in mind, sometimes you might have to provide a structure. When you're not even given a molecular formula, you're given a name. Oh, all of these skills that are going to kind of carry through the course here. So let's imagine that we've got nitrogen trifluoride. To determine the number of electrons, we just add up the number of valence electrons. Periodic table is your best cheat sheet. Nitrogen is in group 5, so that's going to have 5 electrons from our nitrogen. There's 3 fluorine atoms. Each fluorine atom has 7 electrons, so we're going to have 21 total. That's a total of 26 electrons that we're going to need to build our molecule. All right, next step was to piece these together. I'm going to get to this piece down here, but one of the things I want to highlight is the more that you recognize trends in the periodic table, the easier it will be for you to begin piecing these things together. But when we do piece things together, we're going to want to put our least electronegative atom in the center, which is going to be nitrogen. We're going to bond it together with single electrons to our fluorine atoms. Okay, and that accounts for 3 bonds. Doubling that gives us 6 electrons. So remembering over here, we had 26 electrons that we needed to start out with. So I'm going to indicate, all right, we've got 26 electrons that we start out with. I'm going to have, through my single bonds, 6 electrons that are used up. And so I'm going to need to have 20 more electrons be part of this molecule. Remember, those electrons are the glue that needs to hold this together. I need to use all my glue. Not enough and not too much, so we need to make sure we use all of it. So here's how I'd recommend doing this. We're going to start on our periphery. I want you to be able to count by 2s because we're adding electrons as lone pairs of electrons. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18. And now I've added them all on my peripheral atoms. So I'm going to subtract 18 electrons here. Then I'm going to have my lone pairs on my peripheral atoms. And that just leaves me now with 2 electrons left that are going to go on my central atom. So let's put those 2 electrons here. All right. That actually completes our Lewis structure for nitrogen trifluoride. But let's take a look at what I have here in terms of this trends chart. And we're going to learn how to think about things like formal charge. All right, so this represents the group number that we have on the periodic table. And remember that group number also tells us the number of valence electrons. So let's take nitrogen here. Nitrogen's in group 5, so it has 5 electrons. But notice, even though there's 5 electrons that nitrogen is contributing to this structure, this nitrogen atom feels 8 electrons around it. It has a complete octet. So this feel piece really has to do with having a complete octet. So anything that is in group 4, 5, 6, or 7 wants to feel 8 electrons around it. Okay? So what we're going to see here is that this nitrogen feels 8. This fluorine feels 8, even though 2 out of those 8 are shared between those 2 atoms. So this difference between what it feels, what it owns, and what it wants is really important. So everybody wants to have and feel that complete octet. But each of these owns a different number of electrons. Okay? Let's look at this want category now. This want category really has to do with its valence. So that's the valence number. That's how many it came to the molecule with. When we think about what it owns, okay, what it owns is it owns all of any lone pairs, but half of any bonds. So let's take nitrogen here for a second and let's look at this difference between what it owns and what it wants, because the difference between what something owns and what something wants is its formal charge. All right, so let's take this nitrogen atom here. This nitrogen atom wants 5. Let's see how many it owns. 2, and it only owns half of this. So it's 3, 4, 5. So it's got those 2 and then half of each of those 3 bonds. So that's 5 electrons. So what it owns, 5, and what it wants, 5, is equal. So we say that there is no formal charge. There's no discrepancy between want and own. If we go through the same thing with fluorine here, again, this fluorine feels 8, it owns 7, and it wants 7. So the formal charge on this fluorine is 0, and it's the same for all 3 fluorines there. This is what we call an ideal Lewis structure. It has no formal charges. Okay? But one of the things I want to point out from this table, beyond the idea of how we calculated formal charges, is seeing these trends in how groups like to bond. Carbon, or anything in group 4 for that matter, likes to have 4 bonds and no lone pairs. Nitrogen likes to have 3 bonds and 1 lone pair. Oxygen, 2 bonds, 2 lone pairs. And fluorine likes to be 1 bond and 3 lone pairs. Right? And that all has to do with getting to this formal charge of 0. So what we can see here, if these are building blocks, things like carbon and nitrogen like to be in the center because they like to bond to a lot of things. Things like the halogens, or even to some extent, sometimes oxygen, likes to be a peripheral piece, particularly if it looks like this. It's going to be a piece that likes to be on the end of a molecule, or it might be something that's bridging kind of between just 2 other atoms. Nitrogen and carbon like to be more central in the periphery. Okay. So going through and confirming the atoms and electrons that you have, we sort of already did this with this guy, but just to highlight here, when we've got our final structure here, we want to make sure that we have the same number of atoms in our structure as we have in our molecular formula. And go ahead and just double check your number of electrons and make sure that it matches the amount that you were supposed to have. So what I want to do here is just give one more example, and then we're going to talk about how we check octets and formal charges and how this sort of relates to that. So let's build carbon dioxide. All right, carbon dioxide, going a little bit more quickly now. We've got 4 electrons that come from carbon. Each oxygen comes with 6 electrons, so that's a total of 12. So I'm going to have 16 electrons total in my structure. Carbon goes in the center as the least electronegative atom, and I'm going to connect it to my oxygen atoms, and that uses up 4 electrons, and I'm going to have 12 then left over. Let's put those in on the periphery. 2, 4, 6, 8, 10, 12. Looks like I'm done, right? Well, let's take this structure over to the next slide here, and I'm going to show you why this isn't done, and there's a lot that's wrong with this structure. Okay, if we look at what that carbon atom feels around it, it doesn't feel 8 electrons around it. This carbon atom has an incomplete octet, and that's a problem. So an incomplete octet is what we have here. Now each of the oxygen atoms actually has a complete octet. It feels 8 electrons around it, but that carbon atom only feels 4. That's a problem. So when you have that situation, try to move an adjacent lone pair so that we can share it as a bond. And I'm going to show you how we do that here. I'm going to take this lone pair of electrons, and rather than it being totally owned by oxygen, it's going to share it with the adjacent carbon atom. So let's redraw what we'd have here. We'd have oxygen now doubly bonded to carbon. I didn't do anything over on the other side here. And let's see what we have left. I still have an incomplete octet here for carbon. But let's map one other piece on here. Let's go ahead and see what our formal charges would be at this point. Well, this oxygen is actually going to be good. It owns 6 electrons and it wants 6, so that guy's actually good. This oxygen atom here, it actually owns 7, but it only wants 6. So let's think about this. It has one more negative thing than it wants, so it's going to have a -1 formal charge. I know that's a little bit confusing because you think if you're -1, you're in a deficit. No, remember when we're talking about electrons and you have more of them, you actually have a -1 charge. Ooh, this carbon atom's problematic too. This carbon atom owns 3, but it actually wants 4. So it is short one electron, which means it has a formal charge of +1. So we're still not right in terms of a Lewis structure for carbon dioxide. So again, when we have a situation here where adjacent atoms have opposite formal charges, we can think of the phrase have a pair, need to share. So what that means is this oxygen atom has a pair of electrons that it's owning to itself, but it really needs to be sharing with an adjacent atom. So let's go ahead and move another pair of electrons down here and now create what is a correct Lewis structure for carbon dioxide. And if we go through and look at the formal charges again, 0 now on both of those oxygen atoms, carbon has a complete octet and a 0 formal charge. Having minimal or no formal charges, the fewest formal charges, and having nobody with incomplete octets is going to be the best structure that we can have. All right, I want to go through another example here that indicates a concept of drawing resonance structures. So let's draw another example here, and let's think about a substance that has a charge with it. Okay, so I'm going to draw NCS. Actually, let's do NCO here. NCO. NCS would be very similar because carbon and sulfur are below one another in the periodic table, but let's do NCO here. Okay, so let's think about, and I'm going to go through these steps quickly. We're going to have 5 electrons for nitrogen, 4 for carbon, 6 for oxygen, and now I have to add 1 more electron here because that negative charge means I'm going to have 1 more electron than my atoms came in with their original valence electron glue. It's going to give me a total of 16 electrons here. So if I just go ahead and draw and connect everything here with single bonds, that's going to take away 4 electrons. I'm going to have 12 left that I need to place. 2, 4, 6, 8, 10, 12. This is probably looking a little bit similar to the situation we had there with carbon dioxide. So let's go ahead and fix it the same way we fixed carbon dioxide, and I'm going to move these electrons in. They were shared pairs, or they were lone pairs. I'm going to make them into shared pairs. So now I'm going to have this guy right here. I'm going to draw him in the center here. I still have 2 lone pairs on these guys. Everybody has a complete octet. Let's go ahead and check our formal charges here. Oxygen over here is going to have 0 as a formal charge. Carbon here is going to have 0 as a formal charge. Nitrogen, that's going to have a -1 as a formal charge. But you know what? That's important. Remember, this was an ion. The sum of the formal charges have to equal the charge on the species. So this overall has a charge of -1. So that's okay that we have that. So that's another important little piece to remember, is that the overall charge of the molecule must be represented by the sum of the formal charges. All right, I'm going to show you how we draw resonance structures. So resonance structures show the same relative placement of atoms, so the same relative placement of atoms, but we're going to have them differ in the location of those atoms, whether they're as lone pairs of electrons. So just like we sort of moved these electrons around here, we're going to move electrons around in this guy. And I'm going to move them in 2 different directions here. Let me go ahead, I'm going to move this guy up top here, and I'm going to draw with 2 different colors here, different ways to move electrons. Let's imagine first that we move electrons towards oxygen. All right, I'm going to take this pair and I'm going to put it down now to share between carbon and oxygen. Now, one of the things I need to make sure I note is if I did that, I'd have 5 bonds around carbon. I cannot have that. So I need to move a shared pair between carbon and nitrogen now as a lone pair on nitrogen. So I'm going to move that over there. When we draw this movement of electrons, we draw special arrows that I just drew there. These are what we call resonance arrows. So they're going to allow us to move electrons and draw a different structure that shows the same relative placement of atoms, but now a different location of electrons. So see if we can sort of find out what we have here. Oxygen, 3 bonds to carbon, 1 bond to nitrogen, and now I only have 1 lone pair on oxygen, and now I have 3 lone pairs on nitrogen. Okay, so we'll see that we really haven't changed anything on this central carbon atom. It still has 4 bonds around it, so it's still going to have a formal charge of 0. This oxygen atom now picked up a +1 formal charge. And this nitrogen atom, oh boy, that has a -2 formal charge. You'll notice that we still have an overall charge here of -1. But I don't know if we drew a resonance structure that was better or a Lewis structure that was better. Because remember our rules over here? We said the best Lewis structures have the fewest formal charges. I started making more formal charges there. So that might not be the best thing to do. Let's go ahead and try something else here. Let's try moving our electrons in a different way. Rather than moving our electrons towards nitrogen, let's imagine taking the nitrogen's lone pair and let's move those towards oxygen. So if we're going to go like this and move these here, let's draw what that resonance structure would look like. Now I'm going to have a nitrogen that's triply bonded to a carbon, that's singly bonded to an oxygen. Now there's 3 lone pairs on that oxygen, only 1 lone pair on that nitrogen. If we investigate our formal charges on this last resonance structure that we draw, we can see that carbon is still going to have a 0 formal charge. It's got 4 bonds to it. It's got 4 electrons that it owns, 4 that it wants. This oxygen now is going to have a -1 as its formal charge. But as we look at the nitrogen, remembering that nitrogen likes to have 3 bonds and 1 lone pair, that's what it has. So this nitrogen has a formal charge of 0. Like we've seen before, we can add up these formal charges and they're going to equal the overall charge on our molecule. But we actually know enough now to actually rank these 3 possible resonance structures, these 3 Lewis structures. One of them is going to be best, one of them is going to be worst, and one's kind of in the middle. We've already kind of given enough clues that maybe you're good in identifying this guy as being the worst because, like we saw on our last slide here, this has the most formal charges. So when we're looking at having the best Lewis structure, the best Lewis structure has the fewest formal charges. Since this has the most formal charges, that's not going to be the best Lewis structure. But looking at these other 2, it might not be immediately obvious which one is the best Lewis structure. However, if we look at what we have here, we've got a formal charge of -1 on a nitrogen. We've got a formal charge of -1 on an oxygen. Well, if we think about what we know about electronegativities, oxygen is more electronegative than nitrogen. So putting a negative charge on oxygen is actually going to be better than putting a -1 formal charge on nitrogen. So this guy is actually going to be our best Lewis structure. So our best guy is here. All right, I know this has been a lot. I got one more thing I want to share with you, and that's thinking about things that are going to violate the octet rule, or what we call octet rule exceptions. Okay, I'm going to go through 3 scenarios here. First, something that's okay to be deficient or have an incomplete octet. Then situations when it's okay to expand your octet. And then lastly, a situation where we're going to have odd numbers of electrons in our Lewis structures. All right, so let's go through an example of something that would be an octet rule exception where we're going to have an incomplete octet. So for example, if we take BF3 and we think about boron bringing in 3 electrons, we're going to have 21 electrons coming in from our fluorine atoms. That's going to give us 24 total. If we connect everything together with single bonds, that's going to take 6 electrons away. So -6 electrons is going to give me 18 left that I need to place. If I go and I count by 2 and I put my 18 electrons around, I need to stop after I've gone through all my peripheral atoms. Make sure I don't go and put any on boron because that would be too many electrons for this molecule. But if we think about where in the periodic table we find boron, it's in group 3. It only wants to have 3 electrons around it. So having 3 bonds is actually exactly what it wants and gives it a formal charge of 0. So in this case, boron happens to be somewhere in the periodic table where it wants an incomplete octet. So that's okay. Let's talk about things that expand their octet. Here's a quick example, PCl5. Phosphorus comes in with 5 electrons. It's below nitrogen in the periodic table. Each of those chlorines comes with 7 electrons, so that's 35 total electrons. So we've got 40 electrons total that we need to fill in here. I can already see if I start piecing these together, I'm already going to have more than 8 electrons around phosphorus. But if I count for the 10 electrons that I've already put there and I place the remaining 30, that's going to get me through all of my glue, each of these chlorine atoms having the 3 lone pairs that it wants, so it has a 0 formal charge. So this might look a little odd at first, but if we think about where phosphorus is on the periodic table, it actually is in a period that allows us to have d orbitals. And the ability to have d orbitals allows us to have more than 8 electrons. And so it's okay as we get down to things like phosphorus and sulfur, which can expand their octets, unlike nitrogen and oxygen, which we find right above them. So we are going to see things that allow us to expand our octet. All right, one more last example here. When we think about radicals, okay? So let me give an example here to work through with a radical, and that's going to be NO2. So if we go through just our same process here, 5 electrons for nitrogen, 12 electrons for oxygen, 17 electrons. That's an odd number, right? We haven't seen that before. We've always had pairs of electrons that we can add either as bonds or lone pairs. 17 electrons. Well, let's just start building this guy. We've got nitrogen and oxygen here. So let's put everything in. If we take away the 4 electrons we just added, that would be 13 left. 2, 4, 6, 8, 10, 12. Let's put that 13th, lucky 13 there, as a single electron on nitrogen. But I'm starting to see patterns here and recognizing somebody has a pair and is supposed to share. So let's draw our proper resonance structure here so that we have nitrogen having as close to a complete octet as it can. Okay, we're going to have a 0 formal charge there on that oxygen. This guy's going to have a -1 formal charge. But if we look at this nitrogen, that nitrogen only has 4 electrons around it. Remember, it wants 5, so it's short 1 electron, which is how we get a +1 formal charge there. Notice again, our formal charges add up to the overall charge on our molecule, which in this case, there was no charge. But we can't do anything here to fix this adjacent positive and negative informal charges. This guy is just going to live like this. It's going to have +1 and -1 formal charges on these adjacent atoms, and we're also going to have this unique situation of a single electron as a lone electron, not a lone pair, and this is what we call a radical. We don't see that a lot, but these represent molecules that are very unstable. NO2 is actually a really important molecule biologically in your body, okay? So part of that reason is due to its chemical reactivity. All right, so I know this was a lot, but it really is an important skill that we get very good at learning how to draw Lewis structures so that we can build on that through the rest of this learning unit and into the next.